Look up at the night sky. What do you see? A vast, endless expanse of stars, galaxies, and mysteries we're only beginning to understand. But here's something that might make you pause. The universe isn't just expanding. It's stretching faster than we ever imagined, and no one knows exactly why. This isn't just a small adjustment to our cosmic timeline. It's a fundamental shift in how we perceive reality itself. Imagine the fabric of space, not just growing, but accelerating outward, carrying galaxies with it like leaves on a rushing river. And the deeper we look, the more questions arise. What's driving this cosmic speed up? Could there be forces at work beyond anything our laws of physics can explain? Today, we're diving into 30 astonishing facts about the expansion rate of the universe, each one peeling back another layer of this grand mystery. From the moment Edwin Hubble first noticed galaxies racing away from us to the baffling discovery of dark energy pushing everything apart, this journey will challenge everything you thought you knew about space, time, and the ultimate fate of the cosmos. You'll discover how scientists measure distances across billions of light years, why the universe's acceleration defies expectations, and what it means for the future of everything we see. This isn't just about distant stars, it's about the very framework of existence. So buckle up, by the time we're done, the night sky won't look the same to you. The universe is hiding secrets, and together we're about to uncover them. Let's begin. Edwin Hubble wasn't just staring at the night sky, he was rewriting the story of the cosmos. In 1929, he made a discovery that shattered our understanding of the universe. While studying distant galaxies, Hubble noticed something peculiar. Their light wasn't just dimmer, it was shifted toward the red end of the spectrum. This redshift wasn't a quirk of physics, it was a cosmic breadcrumb. The farther away a galaxy was, the faster it appeared to be moving away from us. It was as if space itself was stretching, carrying galaxies along like dots on an inflating balloon. Hubble didn't just observe this expansion, he gave it a number. The Hubble constant, written as h0, became our first cosmic speedometer. It tells us how fast the universe expands for every megaparsec of space, a megaparsec being about 3.26 million light-years. His initial estimate, a staggering 500 kilometers per second per megaparsec. Think of it like this: for every step you take into the cosmos, galaxies sprint away 500 kilometers faster. But here's the twist: Hubble's early measurements were way off. Not because he was wrong, but because the tools of his time couldn't pierce the veil of cosmic dust or account for tricky variables like the motion of stars within galaxies. Today, we've sharpened those numbers with space telescopes like Hubble's namesake and the Gaia mission, peering deeper and more precisely than ever. Modern estimates hover around 70 kilometers per second per megaparsec, far slower than Hubble's guess, but no less mind-bending. Imagine the universe as a rising loaf of raisin bread. As it bakes, every raisin, every galaxy moves away from every other raisin, not because they're speeding through space, but because the dough itself is expanding. That's the Hubble constant in action, and yet, even with cutting-edge tech, this number isn't just a settled fact, it's a frontier. Because when different methods of measuring it disagree, that's not a mistake. It's a mystery, one we're still unraveling. If you think nothing can outrun light, the universe has a surprise for you. Some galaxies are fleeing so fast they appear to break Einstein's ultimate speed limit. But here's the catch: they're not actually moving through space. The culprit, the stretching of space-time itself. Picture a balloon covered in dots, each representing a galaxy. As you inflate it, nearby dots drift apart slowly, while those farther away separate faster. Now imagine blowing up that balloon at an accelerating rate. Dots on opposite sides could rush apart faster than any ant could crawl between them, even though the dots themselves aren't moving across the rubber. That's exactly what's happening on a cosmic scale. When astronomers say a galaxy is receding faster than light, They mean the space between us and that galaxy is stretching so rapidly that the distance grows by over 300,000 kilometers every second. But here's the twist: no signal, no star, no particle is racing through space faster than light. It's the fabric of the universe doing the heavy lifting. This phenomenon, called superluminal recession velocity, bends the rules without breaking them. Einstein's theory of relativity still holds: nothing overtakes light within spacetime. But spacetime itself, that's playing by different rules. The real wonder isn't just the how, but the where. We can actually calculate the boundary where this cosmic magic happens. Roughly 16 billion light-years away, space's expansion hits light speed. Beyond that, galaxies vanish from view forever, their light stretched into oblivion as the space between us and them widens too fast for photons to bridge the gap. It's like a treadmill set to warp speed. Even if you sprint toward the edge, you'll never reach it. This invisible horizon, called the Hubble sphere, marks the point where the universe's expansion wins the race against light itself. And every second, as expansion accelerates, that boundary tightens its grip, stealing more of the cosmos from our future view. What does this mean for the far future? A chilling paradox: the faster the universe grows, the lonelier it gets. Billions of years from now, alien civilizations beyond our local galaxy cluster won't just be unreachable, their light, their very existence, will fade like whispers lost in a hurricane. The night sky, now brimming with galaxies, will someday show only darkness to astronomers of the distant future. All because empty space, the quietest thing imaginable, holds a power greater than light. The universe has a secret ingredient, and it's not stars, planets, or even black holes. It's something far stranger. Picture the cosmos as a vast energy pie sliced into 3 uneven pieces. The smallest sliver, just 5%, is everything we can see and touch: galaxies, stars, your morning coffee. The next slice, 27%, is dark matter, the invisible glue holding galaxies together. But the lion's share, a whopping 68%, belongs to dark energy, the mysterious force stretching space itself faster and faster. Here's what makes dark energy so baffling: it's not pulling matter together like gravity, it's doing the opposite. Imagine blowing up a balloon with a mind of its own, inflating faster the bigger it gets. That's dark energy at work, a cosmic repulsion woven into the fabric of space. And the wildest part, Einstein almost predicted it a century ago with his cosmological constant, a mathematical fudge factor he added to keep the universe static in his equations. When Hubble proved the universe was expanding, Einstein called it his greatest blunder, tossing the idea aside. Turns out he might have been right all along, just for the wrong reasons. Today, we know dark energy isn't a mistake, it's the universe's dominant player. While dark matter sculpts galaxies into cosmic spiderwebs, dark energy stretches those webs apart, a tug of war where one side keeps getting stronger. Think of it like this: if the universe were a car, dark matter would be the brakes, slowing down expansion over billions of years. Dark energy, it's the accelerator pedal being pressed harder with time, speeding us toward a future where distant galaxies vanish like mirages. Yet for all its power, dark energy leaves almost no fingerprints. Unlike dark matter, which betrays its presence by bending light and tugging on stars, dark energy reveals itself only through its cosmic push. Some theories suggest it's the energy of empty space itself, bubbling up from quantum fluctuations. Others propose entirely new physics, like phantom energy or extra dimensions. But one thing's certain: this invisible giant isn't just shaping the universe, it's rewriting its destiny. And the closer we look, the deeper the mystery becomes. In the quest to measure the universe's expansion, astronomers needed something extraordinary, a cosmic ruler precise enough to span billions of light years. Enter Type Ia supernova, the universe's ultimate yardsticks. These cataclysmic explosions occur when a white dwarf, a dense stellar corpse, siphons too much mass from a companion star, crossing a deadly threshold. The result, a thermonuclear detonation so violent it outshines entire galaxies, briefly blazing with a signature brightness so consistent, it's like a lighthouse in the void. No matter where or when they erupt, these supernovae peak at nearly identical luminosities, making them perfect standard candles for measuring cosmic distances. But in 1998, these stellar explosions revealed something far stranger than anyone expected. Two teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were racing to map the universe's expansion using distant supernovae. They assumed gravity would be slowing the cosmos down like a ball tossed upward, gradually losing speed. Instead, the data told a shocking story. The universe wasn't just expanding, it was accelerating. The light from these ancient explosions was dimmer than it should have been, meaning they were farther away than their redshift suggested. Space itself was stretching faster over time, as if some invisible hand had flipped a switch. Perlmutter, Schmidt, and Rees shared the Nobel Prize for this discovery, which upended cosmology overnight. Picture it like marking dots on a balloon, then noticing the dots aren't just drifting apart, they're speeding up as the balloon inflates. Type Ia supernova gave us that critical evidence. Their uniform brightness acts like a cosmic odometer. By comparing how bright they appear to how bright they should be, we can calculate their distance with razor-sharp precision. And when you plot enough of them across the universe, the pattern is undeniable. Dark energy is winning the tug of war against gravity. What makes these explosions so reliable? It's all about physics. Every Type Ia supernova ignites when a white dwarf hits the same explosive limit, about 1.4 times the Sun's mass. Like a bomb with an identical fuse, they detonate with predictable fury. Even subtle differences in their light curves, how they brighten and fade, can be fine-tuned to account for dust or other interference. It's this meticulous calibration that lets astronomers peer back over half the age of the universe, tracing its expansion like rings in a tree trunk. Yet the deeper we look, the more questions arise. Recent studies suggest some Type Ia supernova might not be perfectly uniform, hinting at hidden complexities in how they form. Could there be multiple paths to the same explosive end? Are we missing clues about the behavior of dark energy over time? Every new supernova is a fresh piece of the puzzle, a flickering beacon guiding us through the expanding dark. And as telescopes grow more powerful, these cosmic yardsticks may yet reveal secrets we haven't even dreamed of. To understand the universe's expansion, we need to look at its baby photo, not a grainy ultrasound, but a snapshot frozen in time just 380,000 years after the Big Bang. This ancient light, called the cosmic microwave background, or CMB, blankets the entire sky like a faint whisper of the universe's fiery birth. Imagine stretching a movie frame across the cosmos, one so old it predates stars, galaxies, even atoms as we know them. What's extraordinary isn't just its age, but what it tells us about how space has stretched over billions of years. The Planck satellite, a European Space Agency mission, gave us our sharpest view yet of this primordial glow. Floating nearly 1 million miles from Earth, it mapped the CMB's temperature variations with staggering precision down to millionths of a degree. Those tiny fluctuations, like cosmic fingerprints, aren't random. They're echoes of sound waves rippling through the newborn universe, compressing and stretching matter in dense, rhythmic patterns. Picture dropping pebbles into a pond, but instead of water, the ripples are sculpting the very fabric of space-time. Here's the magic. The spacing between these ripples acts as a cosmic ruler. Just as the distance between frets on a guitar determines its pitch, the scale of these fluctuations reveals how fast the universe was expanding when the CMB formed. Planck's data pegged this rate at about 67 kilometers per second per megaparsec, a number eerily close to what we'd expect if dark energy and dark matter dominate the cosmos. But there's a twist. When we compare this ancient measurement to modern observations of supernova and galaxies, they don't quite match. The universe today seems to be expanding faster than those primordial ripples predict. This discrepancy, called the Hubble tension, isn't just a rounding error. It's a potential crack in our understanding of physics. Could dark energy's push be changing over time? Are there hidden particles or forces tweaking the cosmic scales? The CMB doesn't just show us where we've been, it's a spotlight on what we still don't know. Those faint temperature differences, no warmer than a snowflake's shadow, hold clues to forces that could reshape reality itself. And as new telescopes probe even deeper, we might find that the universe's baby photo has secrets we're only beginning to decode. The Milky Way isn't just drifting through space, it's being hurled at an astonishing 630 kilometers per second, as if some unseen hand has given our galaxy a cosmic shove. For decades, astronomers traced this motion to the Great Attractor, a mysterious concentration of mass pulling us toward the constellation Centaurus. But there's a twist. The Great Attractor alone can't explain the full force behind our galaxy's wild ride. Something else is out there, not pulling but pushing. Enter the dipole repeller, a yawning void so vast and empty, it's essentially a desert in the fabric of space, exerting its influence through sheer absence. Picture the universe as a crowded dance floor. Galaxies cluster where the music's loudest regions dense with stars and dark matter, but between them lie empty spaces, silent and still. The dipole repeller is one of these voids, stretching over hundreds of millions of light years with hardly a galaxy to its name. Like a cosmic game of tug-of-war, this emptiness creates an imbalance. While the Great Attractor pulls us toward its gravitational embrace, the repeller's lack of mass means there's less gravity holding us back. The result: our galaxy gets pushed away from the void, accelerating toward denser regions like a ball rolling downhill. Mapping these flows is like reading cosmic tea leaves. Astronomers track the subtle motions of thousands of galaxies, piecing together how they drift in response to hidden structures. Using redshift surveys and supercomputer simulations, they've reconstructed the gravitational landscape around us, a web of attractors and repellers shaping our local expansion rate. The dipole repeller isn't just a curiosity, it's proof that emptiness can wield as much power as matter when it comes to steering the universe's grand choreography. What's even stranger is how these flows fit into the bigger picture. On small scales, gravity dominates, pulling galaxies into clusters and filaments. But on the largest scales, dark energy's push overwhelms everything, stretching the cosmic web itself. The dipole repeller sits at the crossroads of these forces, a reminder that the universe's expansion isn't uniform. It's a patchwork of pushes and pulls, with voids like this one acting as pressure points in the fabric of space. And as we peer deeper, we're finding more of these shadowy players, each one rewriting the map of our cosmic neighborhood. So next time you gaze at the night sky, remember, the stars aren't just points of light. They're part of a river flowing through space, guided by invisible currents we're only beginning to chart. The Great Attractor may be stealing the spotlight, but the dipole repeller is the silent architect behind the scene, proving that sometimes nothingness speaks louder than mass. Quantum foam and dark energy might sound like science fiction, but they're locked in one of the greatest mismatches in physics, a discrepancy so vast it's been called the vacuum catastrophe. According to quantum theory, empty space isn't really empty. Instead, it's a seething ocean of virtual particles popping in and out of existence, creating what physicists call zero-point energy. These fleeting fluctuations should infuse the vacuum of space with unimaginable energy, enough to bend the universe into pretzels or tear it apart entirely. Calculations suggest the vacuum's energy density should be 10 to the power of 120 times stronger than what we observe as dark energy. That's a 1 followed by 120 zeros, a number so absurdly large it makes the total atoms in the observable universe look like pocket change. This isn't just a rounding error, it's the worst theoretical prediction in the history of science. Imagine calculating the weight of a feather and getting an answer heavier than 1,000 black holes. That's the scale of the mismatch. The puzzle deepens when you realize dark energy, the force accelerating cosmic expansion, is astonishingly weak compared to quantum foam's predicted fury. If the vacuum's energy were even a fraction of what theory suggests, galaxies would never have formed, stars wouldn't shine, reality as we know it wouldn't exist. Yet here we are in a bizarrely balanced universe where dark energy's gentle nudge is just strong enough to matter, but not so strong that it obliterates everything. So where does this colossal error come from? Part of the problem lies in how quantum physics and general relativity talk past each other. Quantum mechanics deals with the incredibly small, where particles behave like waves and probabilities rule. General relativity governs the vast cosmos where space-time bends under mass and energy. But when you try to merge them to calculate vacuum energy, the math explodes into nonsense. It's like using a microscope to study a mountain. The tools don't fit the scale. Some theories suggest unknown symmetries or cancellations might be at work, silently neutralizing most of the vacuum's energy. Others propose radical ideas like extra dimensions siphoning off the excess, or the universe being a holographic projection where deeper laws simplify the chaos. The vacuum catastrophe isn't just a technical hiccup, it's a glaring signpost pointing to gaps in our understanding. Every other major conflict in physics, from Newton's missing planet to the ultraviolet catastrophe that birthed quantum theory, has led to breakthroughs. This one might be no different, whether the answer lies in string theory, loop quantum gravity, or something entirely unforeseen. Solving this puzzle could rewrite the rules of reality itself. Until then, the universe keeps its secrets, balancing on a knife's edge between existence and oblivion, with no one quite sure how. Dark energy might be silently scripting the universe's most dramatic finale, not with a whimper but a violent shredding of reality itself. Picture this: 22 billion years from now, as the last stars flicker out, an invisible force grows stronger, stretching space so ruthlessly it doesn't just separate galaxies. It rips apart planets, molecules, even the fabric of atoms. This is the Big Rip, a doomsday scenario where dark energy doesn't just accelerate expansion but morphs into something far more sinister: phantom energy. Unlike ordinary dark energy, which maintains a steady push, phantom energy's density increases over time, turning the cosmos into its own worst enemy. The math is as chilling as it is elegant. If dark energy's equation of state parameter, a number describing its pressure-to-density ratio, dips below -1, the universe enters a death spiral. Space stretches faster than light can bridge the gaps, first isolating galaxy clusters, then tearing galaxies from their stars. Next, stars are plucked from their planets. Finally, in the last terrifying minutes, phantom energy overpowers the very forces holding atoms together. Nuclei disintegrate, particles are yanked apart faster than they can interact. The universe doesn't just fade, it unravels at the seams. But here's the twist: not all cosmologists buy the Big Rip. Some argue for a gentler end, where dark energy plateaus, leaving islands of matter forever adrift in an icy, expanding void. Others propose a cyclic universe, where expansion eventually reverses in a big crunch, recycling everything into a new Big Bang. String theory even hints at higher dimensional brains colliding like symbols, resetting cosmic history. The truth is, we're staring at a cosmic Rorschach test the same day, yielding wildly different futures based on assumptions we can't yet prove. What makes phantom energy so unnerving isn't just its destructive potential, but how arbitrary it feels. The universe could have chosen any path: endless expansion, cyclical rebirth, or this a finale where emptiness becomes the ultimate destroyer. And while 22 billion years sounds comfortably distant, the clues to our fate are hiding in plain sight. Every supernova, every galaxy survey, every flicker of the cosmic microwave background is a breadcrumb on the trail to understanding whether dark energy is a constant whisper or a gathering storm. Long before galaxies sparkled in the darkness, sound waves raced through the newborn universe like ripples in a pond. These weren't ordinary sound waves, they were pressure oscillations moving at half the speed of light through a seething plasma of particles, a cosmic symphony echoing from the Big Bang itself. When the universe cooled enough for atoms to form, those waves froze in place, etching a subtle pattern into the distribution of matter. Today, we see their fingerprints everywhere, a preferred distance between galaxies, a ghostly imprint spanning 500 million light-years. This is baryon acoustic oscillation, nature's measuring tape woven into the fabric of the cosmos. The Sloan Digital Sky Survey, or SDSS, became our decoder ring for these ancient echoes. By mapping millions of galaxies across a quarter of the sky, astronomers spotted something extraordinary. Galaxies were slightly more likely to be separated by roughly 500 million light-years than any other distance. It's as if the universe had a hidden grid with galaxies clustering at the crests of those primordial waves. Picture dropping pebbles into a pond, then freezing the water at the exact moment the ripples peak. That's how baryon acoustic oscillations work, except the pond is the entire observable universe, and the ripples are the scaffolding for everything we see. What makes these oscillations so powerful is their consistency. Unlike supernova, which rely on stellar physics, or redshift measurements, which can be skewed by local motion, baryon acoustic oscillations depend only on the fundamental laws of sound and gravity. They're a ruler etched into space-time itself. By comparing the apparent size of these patterns in the ancient universe visible in the cosmic microwave background to their size in modern galaxy surveys, astronomers can track how much space has stretched over billions of years. The results, a precise expansion rate that independently confirms dark energy's grip on the cosmos, matching supernova data while sidestepping their uncertainties. But here's where it gets even more intriguing. The SDSS data revealed something unexpected. The universe's large-scale structure isn't just expanding, it's doing so in a way that slightly favors certain directions, as if space itself has a subtle grain. Some scientists speculate this could hint at primordial anomalies, relics from the universe's first moments that tilted the playing field. Others see it as a statistical fluke, a cosmic illusion created by the way we slice the data. Either way, baryon acoustic oscillations aren't just measuring the universe, they're revealing its hidden textures layer by layer, and the best part. This cosmic ruler keeps growing sharper. New surveys like DAISY, the Dark Energy Spectroscopic Instrument, are mapping tens of millions of galaxies with unprecedented precision, turning these faint echoes into a high-definition atlas of expansion. Each measurement tightens the screws on dark energy's behavior, testing whether it's truly constant or if its push changes over time. So next time you hear about galaxy surveys, remember, they're not just cataloging stars. They're listening to the echoes of creation, tuning into a frequency set when the universe was a hot, dense whisper. And every new data point brings us closer to understanding why that whisper is growing louder, faster with each passing billion years. There's a crack in the foundation of cosmology, not a collapse, but a clue. When we measure the universe's expansion using the cosmic microwave background, we get one number, 67 kilometers per second per megaparsec. But when we look at nearby galaxies and supernova, the answer jumps to 73. That 9% gap might not sound like much, but in a field where precision is everything, it's the difference between a whisper and a shout. This is the Hubble tension, and it's either the most exciting problem in modern astrophysics or the most embarrassing. Let's break it down. The cosmic microwave background captures the universe's baby picture, frozen in time when it was just 380,000 years old. Planck's measurements of those primordial ripples are exquisitely precise, like counting the rings of a tree to determine its age. But local measurements using Cepheid variable stars and type Ia supernova act as a cosmic speedometer for the modern universe. Both methods are painstakingly calibrated, yet they stubbornly refuse to agree. It's as if you measured a child's height at birth and again at adulthood, only to find they'd somehow outgrown your predictions by nearly a foot. Some astronomers argue this tension is just a case of muddy data. Maybe interstellar dust is dimming those distant supernovae, tricking us into thinking they're farther away than they are. Or perhaps Cepheid stars, our standard candles, aren't as uniform as we thought, but others suspect something far more thrilling, that we're brushing against physics beyond Einstein's equations. Could dark energy's push be strengthening over time? Might there be an undiscovered particle, like a dark radiation, subtly tweaking the expansion rate? One radical theory even suggests gravity itself behaves differently on cosmic scales, a possibility that would rewrite the rules of the universe. The stakes couldn't be higher. If the tension is real, it could mean our cosmic recipe, 68% dark energy, 27% dark matter, 5% ordinary matter, is missing an ingredient. Picture baking a cake where the flour keeps mysteriously multiplying in the bowl. Every tweak to fix it throws something else off balance. That's where cosmology stands today, staring at a cake that won't rise quite as expected, wondering if we forgot the baking powder, or if the oven runs on entirely new physics. Here's the twist: the Hubble tension isn't just a problem for theorists, it's a call to arms for next-generation telescopes. The James Webb Space Telescope is scrutinizing Cepheid stars with unprecedented clarity, while projects like the Vera-Rubin Observatory will map billions of galaxies to cross-check the expansion rate. Each new dataset is a vote in this cosmic election, and right now the ballots are too close to call. Whether the answer lies in overlooked errors or revolutionary physics, one thing's certain: the universe isn't just expanding, it's keeping secrets. And the Hubble tension, that's our best lead yet. What if dark energy isn't constant, but a shape-shifting force that grows stronger or weaker with time? This isn't just idle speculation. Some cosmologists argue that dark energy might be more like a cosmic mood ring, changing its intensity as the universe ages. Enter quintessence, a theoretical field named after the ancient fifth element philosophers believed permeated the heavens. Unlike the steady push of Einstein's cosmological constant, quintessence ebbs and flows, potentially even switching from repulsive to attractive over billions of years. Picture a dimmer switch for the cosmos. Turn it one way and space accelerates outward. Turn it the other and expansion could slow, or even reverse into a catastrophic big crunch. The evidence for this cosmic roller coaster hides in the subtle dance of distant supernova. When astronomers compare type Ia explosions from different eras, they're not just measuring brightness, they're tracking whether dark energy's push has varied over cosmic history. A telltale sign would be supernova from 7 billion years ago appearing slightly brighter or dimmer than expected, hinting that expansion wasn't accelerating at the same rate back then. While current data favors a steady dark energy, there's wiggle room. Projects like the Dark Energy Survey are combing through thousands of supernova, galaxies, and galaxy clusters, searching for any deviation from the script. Quintessence isn't the only player in this game. Some models propose phantom energy, so extreme it could tear atoms apart, while others imagine dark energy decaying into dark matter, a cosmic handoff that would reshape the universe's fate. The wildest ideas involve quantum fields tunneling between energy states, triggering sudden phase transitions like water freezing into ice. If that happened, the laws of physics themselves might rewrite overnight, leaving stars, planets, and life as we know it stranded in a hostile new reality. Testing these theories means turning the universe into a laboratory. Baryon acoustic oscillations act like a cosmic speed camera, capturing how fast space expanded at different epochs. Gravitational waves from colliding black holes could serve as independent yardsticks, free from the dust and gas that muddle light-based measurements. Even the distribution of galaxy clusters, cosmic cities mapped in 3 dimensions, holds clues about whether dark energy's grip has tightened or loosened over time. The implications are staggering. If dark energy weakens, gravity might eventually win, pulling everything back into a fiery singularity. If it strengthens, the big rip could arrive sooner than anyone predicted. Or perhaps dark energy oscillates, driving cycles of expansion and contraction that endlessly recycle the cosmos. Right now, the data is too faint to say, hidden in the margin of error between competing observations. But the hunt is on, and the answer could rewrite not just our future, but our understanding of reality itself. What if everything we know about the universe's expansion is distorted by an invisible bubble, one we're sitting inside without realizing it? Astronomers call this the Keenan-Barger-Cowie void, or KBC void for short, a cosmic underdensity spanning 2 billion light-years where galaxies are noticeably sparser than the rest of the universe. Picture a vast, invisible snow globe with the Milky Way at its center, surrounded by emptiness on a scale so immense it might be warping our cosmic measurements. The KBC void challenges a cornerstone of cosmology, the Copernican principle, which states that Earth or any observer holds no privileged position in the universe. For centuries, this idea has guided our understanding, assuring us that the cosmos looks roughly the same in all directions, no matter where you're standing. But if we're truly floating in this colossal void, that assumption crumbles. Instead of seeing an average slice of the universe, we'd be peering out from inside a gravitational anomaly, like someone stranded in a desert who assumes the entire world is just as dry. Here's where things get tricky. The void's underdensity means there's less gravity tugging on us from surrounding matter, which could make the local expansion rate appear faster than it truly is. Think of it like stepping off a crowded elevator. The sudden lack of pressure might make you feel lighter, even though your actual weight hasn't changed. Similarly, the KBC void's emptiness might exaggerate our measurements of dark energy's push, creating a false impression of how quickly the universe is stretching beyond our immediate neighborhood. Critics argue the void's existence would violate the cosmological principle so severely, it's statistically unlikely. After all, a 2 billion light-year underdensity centered on us seems suspiciously convenient, like winning the cosmic lottery. Yet surveys of galaxy distributions keep hinting at this strange emptiness, and alternative explanations like undiscovered systematic errors in supernova measurements haven't fully closed the case. The debate isn't just academic. If the KBC void is real, it could force us to recalibrate our understanding of dark energy's strength, or even rethink whether it exists at all. Some theorists propose modified gravity theories that mimic dark energy's effects only in underdense regions, turning the void into a cosmic mirage. Others suggest this might be one of many such bubbles, a fractal structure woven into the universe's fabric that we've only begun to notice. For now, the KBC void remains a tantalizing what-if, a reminder that even our grandest cosmic models are built on assumptions, and sometimes the universe enjoys testing them. Whether it's a statistical fluke or a paradigm-shifting discovery, one thing's certain: the deeper we look, the more we realize how much perspective shapes our place in the cosmos. And sometimes the emptiest spaces hold the loudest questions. Gravitational waves aren't just cosmic ripples. They're silent messengers carrying secrets about the universe's expansion, and in 2017 they delivered a bombshell. When the LIGO and Virgo observatories detected GW170817, the collision of 2 neutron stars 130 million light-years away, they didn't just capture the violent dance of ultra-dense matter. They gave astronomers something far more valuable: a pristine, distance measurement free from the pitfalls of the cosmic ladder, Unlike supernova or Cepheid variables, which rely on chains of assumptions to gauge cosmic distances, gravitational waves encode their own yardstick. The amplitude of these spacetime ripples reveals how much energy was released in the merger, while the signal's duration tells us how far that energy traveled to reach Earth. It's like hearing a song and knowing exactly how loud the singer was at the source, no microphones or guesswork needed. The implications were staggering. By combining the gravitational wave data with the explosion's electromagnetic afterglow, a kilonova spotted by 70 observatories across the globe, scientists pinned down the host galaxy's redshift independently. The result, an expansion rate of around 70 kilometers per second per megaparsec, snugly between supernova-based estimates and Planck's CMB measurements. What makes this so revolutionary is how it bypasses the usual bottlenecks. No need to calibrate standard candles or fret about interstellar dust. Gravitational waves cut through the cosmic noise like a laser through fog, offering a direct glimpse at how space stretches between galaxies. But JW170817 wasn't just a one-off marvel. It proved gravitational waves could serve as universal speedometers capable of cross-checking and potentially reconciling the Hubble tension. Future observatories like the space-based LISA or next-gen ground detectors will catch thousands more mergers, each one a fresh data point in the expansion debate. Picture a network of cosmic buoys, each chirp mapping the universe's growth with ever-sharper precision. And because neutron star collisions often flash in visible light, radio, and X-rays, they're dual messengers, letting us triangulate distances with unprecedented confidence. Yet even this pristine method isn't flawless. The angle at which we observe a merger can skew distance estimates, like trying to judge a flashlight's brightness while squinting through a frosted window. Advanced detectors will minimize this by capturing more signal polarization, sharpening the measurements, but the real promise lies in volume. With enough events, statistical noise smooths out, revealing whether the Hubble tension is a measurement fluke or a crack in physics itself. Every new merger is a vote in this cosmic election, and JW170817 was just the first ballot. The count is underway, and the results could redefine how we measure the universe itself. Hubble's law isn't just an equation, it's the universe's speedometer, and it works like this. The farther away a galaxy is, the faster it's racing away from us. Written as V equals h0 times d, the formula might look simple, but it holds the key to measuring cosmic expansion. Take a galaxy 10 megaparsecs away, that's about 32 million light-years. Multiply that distance by the Hubble constant's current best estimate of 73 kilometers per second per megaparsec, and you get a recession velocity of 730 kilometers per second. That's faster than a bullet fired from a rifle, all because space itself is stretching between us and that distant galaxy. But here's where things get interesting. Hubble's law isn't a straight line forever. At extreme distances, relativity kicks in, warping the simple V equals h0d relationship. Picture a rubber band with marks drawn on it. Stretch it gently and nearby marks move apart slowly, but pull hard enough and the marks near the ends fly away at dizzying speeds. Now imagine that rubber band is space-time and the marks are galaxies. Close by, Hubble's law holds true. Distance and velocity stay neatly proportional. But venture billions of light-years out and the rules change. Space isn't just expanding, it's accelerating thanks to dark energy's push. That means a galaxy 20 megaparsecs away isn't moving at exactly twice the speed of 110 megaparsecs distant. The farther you go, the more the curve bends, like a highway gradually steepening into a runaway ramp. This nonlinearity isn't just a mathematical quirk, it's a fingerprint of the universe's history. When we peer at galaxies so distant their light has traveled for over half the age of the cosmos, their redshifts don't follow the neat linear trend. Instead, they reveal moments when gravity's grip was stronger before dark energy took over. It's like finding fossilized ripples in a riverbed, evidence of a time when the currents flowed differently. And because redshift is our only window into these ancient motions, every deviation from Hubble's straight line forces us to ask, what else is out there, tugging or pushing in ways we haven't yet imagined? The real magic of Hubble's law isn't just in the numbers, it's in how it turns light into a time machine. When we measure a galaxy's redshift, we're not just seeing how fast it's moving now. We're catching a glimpse of how space was stretching when that light began its journey, sometimes billions of years ago. Each redshift is a layered story, a snapshot of expansion at a specific moment in cosmic history. And as our telescopes probe deeper, collecting redshifts from galaxies ever more distant, we're not just mapping space, we're watching the universe grow up, one spectral line at a time. One day, all the galaxies we see today will vanish, not because they've moved, but because the space between us is stretching faster than their light can reach us. Picture standing on a shore as the tide pulls away, watching ships drift over the horizon until their sails disappear one by one. That's the fate awaiting our cosmic neighborhood. Only the ships are galaxies, and the tide is the relentless expansion of the universe. In roughly 100 billion years, every galaxy beyond our local group, Andromeda, the pinwheel, even the spectacular whirlpool, will fade from view, their light stretched into invisibility by the accelerating expansion of space. This isn't just about things getting farther away, it's about the very rules of light breaking down. As space stretches, it drags the wavelengths of photons with it, shifting visible light into infrared, then microwaves, and eventually stretching them so thin they become undetectable. It's like tuning a radio to your favorite station, only to hear the music slow and warp until it fades into static. For distant galaxies, that redshift will eventually cross a point of no return. Even with perfect telescopes, their light will have stretched beyond the longest wavelengths we could ever observe, as if the universe itself hit a cosmic mute button. And here's the lonely twist: the Milky Way won't just lose its neighbors, it'll be marooned in an island universe. Gravity binds us to Andromeda and a handful of smaller galaxies in what's called the local group, but everything else will vanish beyond an unreachable horizon. Future astronomers, if any exist, will peer into the sky and see only darkness where we once charted billions of galaxies. The cosmic microwave background, that faint echo of the Big Bang, will have redshifted into oblivion. Even the evidence of the universe's expansion could disappear, leaving no clues that there was ever anything beyond our galactic backyard. But the most unsettling part: this isolation isn't just a distant possibility, it's already beginning. Galaxies at the edge of our observable universe are slipping away right now, their light growing fainter with each passing century. Telescopes like Hubble and Webb are essentially cosmic archaeologists, capturing relics of a time when the universe was still connected. In a sense, we're living in a privileged era, one where the cosmos is still legible. Future civilizations might never know galaxies existed beyond their own, their night sky reduced to a handful of nearby stars. The universe won't just be expanding, it'll be erasing its own history, leaving us with a sky full of unanswered questions and an ocean of darkness stretching forever. Cepheid variables should be astronomy's perfect yardsticks, pulsating stars whose rhythmic brightness changes reveal their true luminosity with clockwork precision. But beneath this elegant facade lies a simmering controversy that could shake the cosmic distance ladder to its core. At the heart of the debate is a simple question: how do we know how far away these stars really are? The answer hinges on two competing methods, each with passionate defenders and glaring weaknesses. First, there's parallax, the gold standard for measuring stellar distances. Just as your finger seems to shift when viewed alternately through each eye, a star's position appears to wobble as Earth orbits the Sun. Measure that tiny angle, and you can triangulate the star's distance with exquisite precision. Hubble's successor, the Gaia spacecraft, has mapped parallaxes for thousands of Cepheids, anchoring them to the cosmic distance ladder. But here's the catch: beyond a few thousand light-years, parallax measurements get fuzzy, like trying to read a street sign through a snowstorm. That's where the second method swoops in: masers. Imagine a natural laser in space, a cloud of water molecules orbiting a supermassive black hole, emitting microwave beams as precise as atomic clocks. By tracking these masers' motions over years, astronomers can pin down distances to galaxies millions of light-years away, bypassing parallax's limits. The Megamesa Cosmology project used this trick to measure NGC 4258, a galaxy hosting both masers and Cepheids, creating a rare cosmic cross-check. But masers have their own demons. They're vanishingly rare, and their geometry must be just right, like spotting a lighthouse beam aimed perfectly at your telescope. The stakes couldn't be higher when the two methods clash, as they did in 2019, with maser-based distances suggesting a faster expansion rate than parallax. It's not just a technical spat. It's a crisis of cosmic proportions. If Cepheids calibrated by masers are systematically farther away than parallax suggests, the entire distance ladder might need recalibration, tweaking dark energy strength or even the Hubble constant itself. Skeptics argue maser measurements could be skewed by unseen gas clouds warping their signals, while parallax purists face the uncomfortable truth that Gaia's data isn't infallible either. This isn't just academic quibbling. The cosmic distance ladder is built step-by-step: parallax for nearby stars, Cepheids for nearby galaxies, supernova for the distant universe. If the first rung wobbles, the whole structure risks collapse. Some astronomers are now turning to hybrid approaches, using eclipsing binaries or asteroseismology to cross-validate Cepheids. Others are hunting for golden samples, Cepheids in regions where both parallax and maser data overlap, offering a Rosetta Stone for reconciliation. What makes this debate so electrifying is how personal it's become. Conferences have turned into battlegrounds, with researchers wielding error bars like swords. Yet beneath the rivalry lies a shared truth. Both sides are chasing the same elusive prize: a universe that makes sense. Every disagreement, every recalibration, is a step closer to peeling back the layers of cosmic expansion. And until we nail down these flickering stars, the universe's greatest secrets will keep slipping through our fingers, one pulsating mystery at a time. The universe isn't just expanding, it's expanding with near-perfect balance, like a pencil standing on its tip for billions of years without toppling. This cosmic tightrope act is called flatness, and it's one of the most precise fine-tunings in nature. To understand why, picture a graph with two axes, one showing the universe's density, the other its expansion rate. There's a razor-thin line where these values perfectly balance, what cosmologists call the critical density, represented by omega equals 1. Stray even slightly above this line, and gravity would have crumpled the cosmos into a big crunch eons ago. Drift below, and matter would have spread so thin that galaxies never formed. Yet somehow, within 1 part in 10 to the 60th power, that's a 1 followed by 60 zeros, our universe hit this bullseye. This isn't just luck, it's a clue. The mind-boggling precision suggests something extraordinary happened in the universe's first fraction of a second. Enter inflation theory, the idea that space underwent a violent growth spurt, expanding exponentially faster than light itself during the first trillionth of a trillionth of a trillionth of a second. Think of blowing up a balloon from microscopic to cosmic size in less time than it takes light to cross a single atom. This hyper-stretching would have ironed out any primordial wrinkles, smoothing the universe into the flat geometry we observe today. It's like taking a crumpled sheet of paper and stretching it so large that any tiny section feels perfectly smooth to the touch. But flatness isn't just about geometry, it's about destiny. A perfectly balanced omega equals 1 universe keeps expanding forever, but at an ever-slowing rate, barely avoiding collapse or dissipation. It's the cosmological equivalent of a car coasting on an infinite, flat highway, neither rolling backward nor accelerating forward. What's astonishing is how this delicate balance holds across cosmic scales. Whether we measure the cosmic microwave background's temperature fluctuations, map galaxy clusters, or track primordial sound waves, all roads lead back to that magic number 1. The real mystery lies in the alternatives. Why didn't the universe tip into curvature? Some theories propose an infinite multiverse where most universes collapse or evaporate instantly. Ours simply won the cosmic lottery. Others suggest deeper laws that naturally drive omega toward unity during inflation. But perhaps the most startling implication is this: flatness might be evidence that our observable universe is just a tiny patch of something vastly larger, like a single tile in an infinite mosaic. Every measurement we make, from supernova to gravitational waves, keeps pointing us back to this extraordinary equilibrium, a universe balanced on a knife's edge, its expansion and density locked in perfect harmony since the first unimaginable moments of time. The James Webb Space Telescope was supposed to clarify the universe's early chapters. Instead, it handed astronomers a plot twist they're still scrambling to explain. When JWST turned its gold-plated eye toward the cosmic dawn, it spotted galaxies so massive, so mature, they had no business existing when the universe was just 300 million years young. These cosmic toddlers, brimming with ancient starlight, weigh as much as 100 billion suns, comparable to our Milky Way, but born in a fraction of the time. If the standard model of cosmology is correct, there simply wasn't enough time after the Big Bang for gravity to gather so much matter, let alone forge stars and galaxies of such staggering scale. It's like finding a skyscraper in the ruins of a civilization that only just discovered the wheel. What makes these galaxies even more baffling is their structure. Many display intricate spiral arms, dense bulges, and even evidence of supermassive black holes, features that, according to simulations, should take billions of years to develop. Yet here they are, flaunting their sophistication in an era when the universe was still just 2% of its current age. Some theories suggest these galaxies grew from seeds far heavier than our models predict. Perhaps colossal clouds of gas collapsing directly into black holes, or dark matter clumping faster than expected. Others propose more radical ideas, that the universe's expansion history isn't what we think, or that dark energy's influence kicked in earlier than presumed, warping the timeline of cosmic evolution. The implications ripple far beyond early galaxies. If the standard lambda model lambda cold dark matter, the reigning framework of cosmology, can't account for these precocious giants, we might need to tweak its ingredients. Maybe dark matter interacts more strongly with itself, accelerating galaxy formation. Or perhaps the cosmological constant representing dark energy isn't constant at all, but varied wildly in the universe's infancy. JWST discoveries have even revived fringe ideas like modified gravity theories, which attempt to explain galactic behavior without invoking dark matter at all. Yet for all the excitement, there are cautionary notes. Some astronomers argue these early giants might be rarer than they appear, their brightness amplified by gravitational lensing or exotic stellar populations. Others suggest our simulations simply underestimate how quickly stars could form in the denser, hotter environment of the young cosmos. What's certain is that JWST has cracked open a door to the universe's first moments, revealing a nursery far stranger and more vibrant than anyone predicted. Every new spectrum, every redshift measurement, is a fresh clue in this cosmic whodunit, one that might rewrite not just the story of galaxies, but the very laws governing their birth. As the data pours in, one thing becomes clear: our universe's childhood was anything but simple. Whether these galaxies force a revision of lambdactum or unveil entirely new physics, they prove that even our best models are just sketches of a reality far richer and more surprising than we've dared to imagine. And somewhere in that ancient starlight, the answers are waiting, if we're bold enough to rethink everything we know. The universe is supposed to look the same in every direction, no favorite spots, no cosmic north or south. That's the cosmological principle, the idea that on the largest scales, matter and energy are spread smoothly and evenly like batter in a well-mixed cake. But what if we're wrong? What if, when we zoom out far enough, the cosmos reveals a hidden lumpiness, a structure so vast it defies everything we thought we knew? Quasars, those brilliant beacons powered by ravenous black holes, should be scattered randomly across the sky if the universe is truly uniform. Yet when astronomers mapped over 100,000 of them, they spotted strange, thread-like patterns stretching billions of light years, forming a grid so colossal it could swallow our local galactic neighborhood 1,000 times over. Gamma-ray bursts, the universe's most violent explosions, tell a similar story. These fleeting flashes of energy should pop off randomly like fireflies in a summer field. Instead, they cluster along invisible lines, tracing out structures that challenge the very definition of large scale. Then there's the Great Arc, a crescent of galaxies so enormous it spans 3 billion light-years, a cosmic continent drifting in the void. Spotting something so immense in a supposedly uniform universe is like drawing a straight line across the Pacific Ocean and finding it perfectly flat, only to realize it's actually the rim of a teacup you hadn't noticed until now. These anomalies aren't just statistical flukes, they're potential cracks in cosmology's foundation. If matter clumps on scales this vast, does dark energy behave differently in these regions? Could the Hubble tension itself be a side effect of living in a cosmic outlier? Critics argue these structures might be illusions, tricks of perspective where chance alignments mimic patterns. But as surveys grow larger and simulations sharper, the evidence keeps stacking up. The universe might not be the well-mixed batter we imagined. Instead, it could be more like a fractal, with hidden layers of order repeating at scales so grand we've only just begun to notice. And if that's true, the cosmological principle isn't just a minor tweak away from being fixed. It's a signpost pointing to a cosmos far stranger than we ever dared to assume. Neutrinos are the universe's most elusive particles. Billions pass through your body every second, ghostly and unnoticed. For decades, physicists assumed they were massless, zipping through space at the speed of light. But in 1998, two discoveries rocked cosmology: dark energy's accelerating push and the revelation that neutrinos, against all expectations, have a tiny but measurable mass. This cosmic coincidence wasn't just a footnote. It meant these shadowy particles could be quietly tugging on the universe's expansion, adding a subtle drag to dark energy's runaway sprint. The key lies in neutrino oscillations, the phenomenon that earned researchers the Nobel Prize. As neutrinos travel, they shape-shift between three flavors: electron, muon, and tau, like a chameleon cycling through colors. This metamorphosis only happens if neutrinos have mass, however slight. When scientists finally pinned down that mass, it was staggeringly small. The heaviest neutrino is at least 6 million times lighter than an electron. But across the cosmos, their numbers are staggering. The Big Bang flooded space with roughly 300 neutrinos per cubic centimeter, outnumbering atoms by 1 billion to 1. Multiply even a whisper of mass by those trillions upon trillions of particles, and suddenly, neutrinos contribute as much to the universe's mass density as all the stars combined. Here's where expansion gets interesting. While dark energy stretches space outward, neutrinos act as cosmic ballast, their collective gravity gently braking that expansion. Imagine blowing up a balloon covered in sand. The rubber wants to expand, but the grains tug back, slowing the process. Neutrinos work the same way, their gravity countering dark energy's push just enough to tweak the universe's expansion history. Current estimates suggest neutrinos reduce the expansion rate by roughly 0.5%, a tiny effect but one that could tip the scales in precision cosmology. Yet neutrinos aren't like ordinary matter. They're relativistic, meaning they zip around at near light speeds, especially in the universe's hotter, denser youth. This changes how they interact with gravity. While cold dark matter clumps into galaxies, neutrinos stream through them like fog through a sieve, smoothing out structures on vast scales. This unique behavior means their gravitational influence evolves over cosmic time weak in the early universe when they moved too fast to cluster, stronger today as they slow down and linger. Some models even suggest this transition could mimic dark energy's effects, potentially muddying our measurements of expansion. The deeper mystery, we still don't know neutrino masses precisely. Experiments like Katrin and future cosmic microwave background studies aim to pin them down, but for now, they remain floating variables in cosmology's equations. Could heavier neutrinos explain part of the Hubble tension? Might exotic, sterile neutrinos' hypothetical, even more elusive cousins lurk in the shadows? Every fraction of an electron volt matters when calculating how these phantoms sculpt the cosmos. What's certain is this: in the grand tug of war between dark energy's push and gravity's pull, neutrinos are the stealthy middleweights, too light to dominate, too numerous to ignore. Their discovery didn't just rewrite particle physics, it added a hidden layer to the universe's expansion story, one we're still deciphering photon by photon, oscillation by oscillation. And as we refine our measurements, these ghostly particles might yet reveal secrets that shake the foundations of cosmology itself. Long before galaxies took shape, the universe was a seething plasma, ringing with sound waves that raced outward at over half the speed of light. These weren't ordinary sound waves, they were pressure oscillations trapped in a tug of war between gravity's inward pull and radiation's explosive push. As the infant cosmos cooled around 380,000 years old, those waves suddenly froze in place, etching their signature into the distribution of matter like sonic fossils. Today, we see their legacy as a faint but unmistakable bump in galaxy surveys, a preferred separation of about 490,000 light-years, a cosmic yardstick known as the Sound Horizon Scale. This imprint works like nature's ruler. When astronomers map millions of galaxies, they notice an odd trend: pairs of galaxies are slightly more likely to be separated by this exact distance than any other. It's as if the universe has a hidden grid with galaxies clustering at the crests of those ancient sound waves. Picture dropping a handful of pebbles into a pond and letting the ripples freeze mid-motion. The distance between wave peaks becomes a fixed reference, unchanged by time. That's what the sound horizon offers, a snapshot of the universe's expansion at the exact moment atoms formed and light broke free. The magic lies in its precision. Unlike supernova or Cepheid stars, which depend on stellar physics, the sound horizon is set by fundamental constants: the speed of sound in primordial plasma and the universe's density at recombination. These values are etched into the cosmic microwave background with razor-sharp clarity. By comparing the apparent size of these ripples in the CMB to their scale in modern galaxy surveys, astronomers can measure how much space has stretched over billions of years. It's like finding a fossilized footprint and comparing it to a fresh one. The difference reveals how much the ground has shifted, but here's where it gets even more fascinating. The sound horizon isn't just a relic, it's a Rosetta Stone for dark energy. When combined with supernova data, it reveals how expansion accelerated over cosmic time. Those frozen sound waves tell us the universe initially slowed under gravity's grip, then hit a tipping point around 5 billion years ago when dark energy took the wheel. The 490,000 light-year bump becomes a speed bump in spacetime, marking the moment the cosmos switched from deceleration to overdrive. Yet this pristine ruler isn't without quirks. Recent surveys like DAISY have uncovered subtle anisotropies, hints that the sound horizon might vary slightly depending on which direction we look. Could this be a statistical fluke or evidence of primordial imbalances in the universe's infancy? Some theorists speculate it might trace back to inflationary irregularities, while others wonder if dark energy's push isn't perfectly uniform. Every new galaxy map adds another layer to the puzzle, refining our measurements while deepening the mystery. What makes the sound horizon so indispensable is its independence. While other methods chain together assumptions parallax to Cepheids to supernova, this cosmic fingerprint stands alone, a direct link between the universe's birth cries and its present expansion. Future missions, like ESA's Euclid telescope, will exploit this to test dark energy's constancy with unprecedented rigor. Because if those 490,000 light-year ripples start whispering secrets we don't expect, it might mean the universe's expansion story is far stranger than we've dared to imagine. Black holes aren't just cosmic vacuum cleaners, they're also slowly leaking energy, and that evaporation could rewrite the far future of the universe. Stephen Hawking stunned the physics world when he calculated that black holes aren't entirely black. Due to quantum effects near their event horizons, they emit a faint glow of particles now called Hawking radiation. This process isn't fast. A standard stellar mass black hole would take longer than the current age of the universe to evaporate. But given enough time, even the mightiest black holes will dissolve into a whisper of radiation. Now imagine this happening across the cosmos trillions of years from now, when galaxies have faded and dark energy has stretched space into an unimaginably vast emptiness. Could this slow trickle of energy from dying black holes become the universe's last flickering counterbalance to dark energy's relentless expansion? The math is tantalizing. As black holes evaporate, they convert mass directly into energy according to Einstein's famous equation E equals mc squared. Supermassive black holes, those billion solar mass behemoths at galactic centers, would release truly staggering amounts of radiation over their final epochs. Some theories suggest this energy could act like a cosmic pressure, opposing dark energy's stretching of space. Picture a balloon inflating while someone inside blows puffs of air outward. The two forces might reach an uneasy equilibrium, slowing the rate at which the universe tears itself apart. But there's a catch. Hawking radiation isn't a steady stream. It accelerates as black holes shrink, becoming a runaway explosion in their final seconds. This means most of the energy release happens in a brief crescendo long after the universe has already become unfathomably cold and empty. By then, dark energy's grip may be too strong for even these final bursts to matter. Worse still, the radiation itself adds to the universe's energy content, potentially fueling expansion rather than resisting it. It's like trying to stop a forest fire by throwing gasoline. The cure might accelerate the disease. The wild card is quantum gravity. Our current theories break down at the moment of a black hole's final evaporation, when temperatures reach Planck scale intensities. Some models predict miniature black holes could leave behind stable relics packed with concentrated dark energy. Others suggest the radiation might carry hidden information about spacetime's fundamental structure. If these remnants or radiation patterns interact unexpectedly with the cosmological constant, the mathematical representation of dark energy, all bets are off. While Hawking radiation likely won't save the universe from dark energy's victory, it adds a poetic twist to the cosmic endgame. Those terrifying monsters of gravity, the black holes, may ultimately become the universe's last light sources, flickering against the encroaching dark like candles in an endless night. Their slow demise ensures that even in the farthest future, energy still flows, transformations still occur, and the cosmos never quite settles into perfect stillness. The universe's final chapters won't be written in darkness alone, but in the fading glow of black holes exhaling their last breaths across the infinite void. The universe doesn't expand like a perfectly inflating balloon. It's more like rising dough studded with raisins, where some regions stretch faster than others. This cosmic unevenness creates a breathtaking divide between the vast, empty voids and the dense galaxy clusters, each obeying different rules of expansion. Picture a spider web after rain. Some threads sag under water droplets while others stay taut. In the cosmic web, clusters act like those weighted droplets, their immense gravity resisting dark energy's pull, while voids, the empty stretches between filaments, stretch unchecked, accelerating into ever-growing deserts of spacetime. Galaxy clusters are the universe's metropolises, where hundreds or thousands of galaxies huddle together, bound by dark matter's invisible scaffolding. Their gravity is so strong, it creates a local tug of war against dark energy's outward push. Imagine holding two ends of a rubber band while a friend pulls them apart. Your grip represents a cluster's gravity, fighting to keep space from stretching. This resistance means expansion happens slower here, like time flowing at half speed. The Virgo cluster, our nearest neighbor just 55 million light-years away, barely feels the universe's stretch compared to isolated galaxies. But cross into a void like the Boötes void, a spherical emptiness spanning 330 million light-years with only 60 galaxies, and the rules change. Here, the absence of matter means gravity's grip weakens to a whisper, letting dark energy dominate. Without galaxies or dark matter to anchor it, space in these regions expands up to 10% faster than the cosmic average. It's like stepping into a wind tunnel after being in still air. Suddenly, everything accelerates. This divide isn't just theoretical. Astronomers measure it by tracking galaxies on the edges of voids, watching their light red shift more dramatically than those near clusters, as if spacetime itself is sliding downhill into the emptiness. The cosmic web structure magnifies this effect. Voids aren't random bubbles, they're interconnected, forming a honeycomb of nothingness that stretches across billions of light-years. As they grow, they squeeze the surrounding matter into ever denser filaments and clusters, like water forced between expanding cracks in ice. This feedback loop creates a universe where your local address determines how fast you're moving away from everything else. A galaxy floating deep in a void might see neighboring galaxies vanish over cosmic horizons, while one in a rich cluster watches its neighbors remain visible for eons longer. What's startling is how this divide challenges our intuition. We might assume the universe's expansion is a uniform force, like a tide rising equally everywhere. Instead, it's a fractured landscape where gravity and dark energy wage a slow-motion battle, with emptiness as the ultimate battleground. Future telescopes like Euclid aim to map this cosmic terrain in 3D, revealing whether dark energy's strength varies in these regions. Because if voids accelerate faster than we predict, it might mean dark energy isn't just a constant background force. It could be something far stranger, shaped by the very emptiness it expands. Dark energy might not be the universe's final word after all. Some theories suggest this mysterious force could decay, transforming into particles or even another form of energy that could rewrite the fate of everything. Picture a pressure valve slowly releasing steam. What if dark energy isn't a constant, unyielding push, but a reservoir slowly leaking into something else? One compelling idea involves action like particles, hypothetical relics from the early universe that could interact with dark energy in unexpected ways. These ultralight particles, far lighter than electrons, might act like cosmic sponges, absorbing dark energy's repulsive force and converting it into ordinary matter over billions of years. It's as if the universe's accelerator pedal isn't stuck at full throttle but could someday ease up, allowing gravity to regain some control. The math behind this is delicate but tantalizing. If dark energy decays at just the right rate, its density would decrease over time, gradually reducing its push against gravity. Instead of racing toward eternal expansion or a catastrophic big rip, the cosmos could find equilibrium, a gentle balance where matter and energy reach a truce. This scenario, sometimes called dark energy dilution, hinges on quantum fields that aren't static but dynamic, evolving alongside the universe itself. Actions originally proposed to solve puzzles in particle physics could be the missing link. these wispy particles might interact with the same quantum vacuum that fuels dark energy, subtly siphoning its strength into particles we can't yet detect. But there's another, wilder possibility: vacuum metastability. Imagine the universe's current vacuum state the underlying energy of empty space. Isn't the lowest possible energy level but a false plateau? Like a ball resting on a hillside instead of the valley below, it could be stable for now but destined to eventually roll downhill. If dark energy is tied to this precarious state, a quantum fluctuation could trigger a catastrophic phase transition, rewriting the laws of physics in an instant. In this scenario, dark energy wouldn't just decay, it would collapse, releasing an unfathomable burst of energy that resets the cosmic clock. A new vacuum state could emerge with entirely different fundamental constants, potentially birthing a new universe with its own rules. The stakes couldn't be higher. If dark energy is truly metastable, its decay wouldn't be a slow fade but a sudden, irreversible shift. The transition could propagate at light speed, erasing everything in its path without warning. One moment, the universe expands as usual. The next, a wall of annihilation sweeps through space, leaving nothing recognizable behind. It's a cosmic game of Russian roulette where the trigger might not be pulled for billions of years or could happen tomorrow. Yet for all its drama, this idea isn't pure speculation. Particle colliders like the Large Hadron Collider and future experiments hunting for actions could provide clues. If these particles exist, their properties might reveal whether dark energy's grip is eternal or ephemeral. Similarly, precise measurements of the expansion rate over time could show telltale signs of decay, like a slow leak in a tire. What makes these theories so electrifying isn't just their audacity, it's their reminder that dark energy, for all its dominance, might be a temporary chapter in the universe's story. The cosmos could be far more dynamic than we've dared to imagine, with forces that rise, fall, and transform over epochs we're only beginning to map. Whether through actions, vacuum decay, or something entirely unforeseen, the end of dark energy's reign might not mean oblivion, but rebirth. Hydrogen, the simplest and most abundant element in the universe, hides a whisper, a faint radio hum at 21 centimeters that could unlock the darkest chapters of cosmic expansion. Every hydrogen atom spins like a tiny top, and when its electron flips direction, it emits this signature wavelength. It's a heartbeat echoing across the void, one that's been pulsing since the first atoms formed. Now, telescopes like the Square Kilometre Array, or SCAR, a sprawling network of radio dishes spanning continents, are tuning into these whispers, not just to listen, but to trace how space itself has stretched over nearly the entirety of cosmic history. The genius lies in redshift. As the universe expands, that 21-centimeter line gets stretched too, shifting toward longer, redder wavelengths. By measuring how much each hydrogen signal has shifted, astronomers can reconstruct how fast space was expanding when the light began its journey billions of years ago. Unlike stars or galaxies, hydrogen is everywhere, painting the cosmic web in strokes of radio static. SKA won't just spot a few landmarks, it'll chart entire epochs, from the cosmic dawn when the first stars flickered on, through the dark ages, all the way to the modern universe. Imagine unrolling a scroll where every inch represents a billion years, and every atom's hum records the exact tension of space at that moment. But here's the real magic. Hydrogen lets us peer into eras even the James Webb Space Telescope can't touch. Before stars ignited, the universe was a fog of neutral hydrogen, opaque to visible light but singing loud in radio waves. SKA will slice through that fog, mapping how clumps of gas flowed and clustered under gravity's pull, and how dark energy later pried them apart. It's like finding fossilized ripples in a pond that froze long before the first fish swam. Some of these signals are so ancient, they've been redshifted from 21 centimeters to over 2 meters, stretched by eons of expansion into a base note too deep for most telescopes to hear. The scale of this project is staggering. SKA's thousands of antennas will generate more data in a day than the entire global internet, sifting through cosmic static for whispers buried under noise. To isolate the signal, engineers must filter out everything from Earth's radio chatter to the crackle of distant quasars. It's like trying to hear a single raindrop in a hurricane, but if it works, the payoff could rewrite cosmology. Hydrogen's redshift map might reveal whether dark energy's push has changed over time, or if unknown forces altered expansion during the universe's adolescence. And there's a tantalizing wild card. Hydrogen could expose anomalies in gravity itself. If Einstein's general relativity holds, the gas should clump in predictable ways at different redshifts. But if gravity behaves differently on cosmic scales, say, due to hidden dimensions or modified theories, hydrogen's distribution will bear the fingerprints. SKA's 3D maps might even uncover primordial ripples from inflation, the universe's violent growth spurt in its first trillionth of a second. What makes this approach so revolutionary is its continuity. While supernova and Cepheids offer snapshots, hydrogen provides a film strip, capturing expansion frame by frame across nearly 13 billion years. Future astronomers might scroll through these radio maps like flipping pages in a cosmic flipbook, watching space itself stretch and accelerate in real time. And somewhere in that data, hidden in the hum of a billion atoms, could be the answer to the ultimate question: where is the universe rushing to, and will it ever look back? The universe might be stretching uniformly in all directions, except where it isn't. Within about 100 million light-years of the Milky Way, the Hubble flow, the smooth expansion of space predicted by the Hubble constant, gets messy. Here, gravity takes the wheel, bending and twisting the motion of galaxies like a cosmic game of tug-of-war. The culprit, the colossal mass of the Virgo supercluster, a sprawling family of galaxies anchored by the Virgo cluster, which yanks everything nearby off course with its immense gravitational pull. Picture a river flowing steadily downstream. That's the Hubble flow, carrying galaxies outward as space expands. Now drop a boulder into that river. The water nearest the rock swirls and eddies, while the current farther out remains unaffected. The Virgo supercluster is that boulder. Its sheer mass, equivalent to over a quadrillion suns, warps spacetime so severely that galaxies within its reach don't just drift outward with the universe's expansion. They're drawn toward Virgo's gravitational well, creating what astronomers call peculiar velocities. These are deviations from the expected Hubble flow, where galaxies move unpredictably, like leaves caught in a gust rather than floating on a steady tide. Our own Milky Way is part of this gravitational dance. Measurements show we're hurtling toward Virgo at roughly 300 kilometers per second, a motion superimposed on the universe's broader expansion. Nearby galaxies like Andromeda exhibit similar quirks, their paths bent by local pulls. In fact, the entire local group, our galactic neighborhood, is being tugged not just by Virgo, but by an even larger structure, the Laniakea supercluster, a web of galaxies 500 million light-years wide. Laniakea, meaning immense heaven in Hawaiian, acts as a gravitational watershed, directing the flow of galaxies like rivers into a basin. Mapping these deviations is like reconstructing a crime scene from bullet trajectories. By tracking galaxy motions, astronomers can triangulate the hidden mass pulling them off course. The Virgo supercluster's influence fades beyond 100 million light-years, where the Hubble flow finally smooths out. But closer in, peculiar velocities dominate. Some galaxies race toward us, others veer sideways, their paths tracing the invisible contours of dark matter filaments and cluster cores. Without accounting for these distortions, local measurements of the Hubble constant would be wildly off, like trying to calculate a car's speed while ignoring the fact it's swerving to avoid potholes. Yet these deviations aren't just noise, they're clues. Peculiar velocities let us weigh superclusters, probe dark matter's distribution, and even test gravity itself. When galaxies move faster than local mass can explain, it might hint at unseen structures or flaws in our gravitational models. The Virgo-centric flow is just one thread in a vast cosmic tapestry, where every tug and twist reveals how deeply interconnected the universe truly is, not just expanding, but breathing, pulsing, and dancing to the tune of gravity's unseen hand. What if the Hubble constant isn't constant at all? The idea might sound heretical after all. Edwin Hubble's namesake equation treats this cosmic speedometer as a fixed number. But what if it subtly shifts over time, like a car's cruise control that doesn't quite hold steady? This isn't just a tweak to the math, it's a potential escape hatch from the Hubble tension, that nagging mismatch between early and late universe expansion rates. One compelling solution lies in early dark energy, a hypothetical burst of repulsive force that might have flared up during the universe's first 100,000 years before vanishing without a trace. Picture the cosmos as a rocket launch. Standard cosmology says the engines fired once during inflation, then coasted until dark energy kicked in billions of years later. Early dark energy suggests there was a second, shorter burn just as the first atoms were forming. This extra push would have temporarily juiced up the universe's expansion, altering the sound horizon scale imprinted on the cosmic microwave background. When we measure that ancient imprint today, it would make the early universe appear to have expanded slower than it actually did. Precisely the discrepancy we see between Planck's SIMB measurements and modern supernova data. It's like finding a speedometer reading from a road trip that doesn't account for a momentary detour through a speed zone. Modified gravity offers another twist. Einstein's general relativity has passed every test thrown at it, from bending starlight to predicting black holes. But what if it slightly misfires on cosmic scales? Some theories, like scalar tensor gravity or massive gravity, introduce subtle adjustments to how mass curves spacetime. These tweaks could make gravity stronger in the early universe's dense environment, slowing expansion more than standard models predict. Later, as matter thinned out, gravity's grip would weaken, letting dark energy appear stronger today. The result, a Hubble constant that effectively runs with cosmic time, high in the past and lower now. Think of it as a rubber band that stiffens when stretched. The more the universe expands, the less gravity resists, creating the illusion of acceleration without requiring extra dark energy. The beauty of these ideas is how they turn the Hubble tension into a clue rather than a crisis. Early dark energy leaves fingerprints in the cosmic microwave background's polarization patterns, while modified gravity alters how galaxy clusters free fall through space. Current data can't yet confirm either, but next-generation telescopes like Simon's Observatory and the Vera Rubin Observatory are hunting for these subtle signatures. Yet the boldest proposals combine both approaches. Imagine a universe where dark energy pulses in epochs and gravity's rules evolve, a cosmos with multiple gears shifting over time. If true, our constant isn't just running, it's sprinting through hidden phases, each leaving its mark on the fabric of space. The Hubble tension might not be an error to fix, but a portal to deeper physics, whispering that our cosmic speedometer was never meant to stay still. The cosmic microwave background should be a chaotic snapshot of the universe's violent infancy, a roiling plasma of shockwaves, turbulence, and gravitational storms. Instead, it's eerily smooth, with temperature variations so slight they're barely 1 part in 100,000. It's like expecting a stormy ocean in a hurricane and finding the surface calm as glass, every wave ironed out to near perfection. This quietness is one of cosmology's deepest puzzles. How did the universe's frenetic early motions vanish without a trace? The answer lies in inflation, the universe's explosive growth spurt in its first trillionth of a second. Picture a balloon inflating from subatomic size to larger than the observable universe in less time than it takes light to cross a proton. any primordial wrinkles, density variations, whirlpools of plasma, or gravitational ripples would have been stretched so thin they became nearly imperceptible. It's like zooming in on a crumpled sheet of paper until the folds vanish into flatness. This hyper-stretching didn't just smooth the cosmos, it set the stage for everything that followed. Those minuscule 1 part in 100,000 fluctuations became the seeds for all structure galaxies, clusters, and the cosmic web itself, like slight variations in dough determining where raisins cluster in baked bread. Yet the CMB's tranquility is even stranger when you consider what came before. Quantum mechanics dictates that the infant universe should have been a seething foam of particle-antiparticle pairs popping in and out of existence, each fluctuation potentially distorting spacetime. Add to this the violent energy of phase transitions, moments when the fundamental forces split apart, and the early cosmos should have been a cacophony of chaos. Instead, inflation's relentless expansion acted like cosmic noise-canceling headphones, drowning out the turbulence until only the faintest whisper remained. The precision of this smoothing is unnerving. If the fluctuations had been slightly stronger, matter would have clumped too aggressively, collapsing into a maelstrom of black holes. Slightly weaker, and gravity couldn't gather galaxies at all. This fine-tuning hints at something profound. The universe didn't just evolve randomly. Its initial conditions were dialed to an almost impossible precision, as if following a hidden blueprint. Some theorists argue this points to a deeper law, perhaps a multiverse where countless universes bloom with different properties, and we simply inhabit one where the numbers allowed stars and planets to form. Others see it as evidence of an as-yet unknown symmetry governing the Big Bang. The CMB's quiet also hides a subtle asymmetry. One hemisphere is very slightly warmer than the other, and there's a mysterious cold spot spanning billions of light years. These anomalies are too large to fit neatly into inflation's predictions, like finding a fingerprint on a freshly wiped mirror. Could they be scars from a pre-inflation era when the universe was still tangled in higher dimensional strings, or evidence of a collision with another universe bubbling beyond our own? The anomalies are faint enough to dismiss as statistical noise, but persistent enough to keep theorists awake at night. What makes this cosmic silence so powerful is how much it says with so little. Those tiny temperature variations aren't just relics, they're the universe's first language, spelling out its origin in a code we're still deciphering. Every new CMB map sharpens the message, revealing not just how the cosmos began, but how finely tuned its infancy had to be for us to exist at all. The quiet, it turns out, speaks volumes. Einstein's gravity bends the cosmos on large scales, while quantum mechanics rules the tiny world of particles. But where these two titans collide, our understanding shatters. What happens to the universe's expansion when spacetime itself becomes granular, breaking into indivisible quantum threads? Loop quantum cosmology dares to answer this by reimagining the Big Bang not as a singularity but as a cosmic bounce. Picture the universe not exploding from nothing, but rebounding from a previous collapse like a spring compressed to its limit. In this radical rewrite, dark energy's acceleration could be an illusion, an aftershock of that primordial bounce, stretching space in ways standard relativity can't explain. The key lies in spacetime's quantum structure. Just as a fabric appears smooth until you zoom in to see its woven threads, loop quantum gravity suggests spacetime is knitted from finite loops at microscopic scales. These loops can't stretch infinitely, meaning the universe's expansion hits a quantum speed limit. As space approaches this limit, strange physics kicks in. Gravity briefly becomes repulsive, mimicking dark energy's effects without needing any mysterious substance. It's like a car that automatically brakes as it nears top speed. The universe self-regulates its expansion through quantum geometry alone. String theory offers a different twist. In this framework, the fundamental particles aren't dots but vibrating strings, and dark energy might emerge from extra dimensions curled up like hidden origami. Imagine space as a vast ocean with dark energy as underwater currents driven by unseen depths. Certain string theory models suggest these extra dimensions could leak gravitational pressure, subtly altering how our three-dimensional space expands. Some versions even replace dark energy with quintessence, a dynamic field that evolves over time, potentially explaining why expansion rates don't quite match standard predictions. Both theories face hurdles. Loop quantum cosmology's bounce lacks definitive observational proof, though it leaves subtle fingerprints in the cosmic microwave background's polarization patterns. String theory's math is so complex it predicts countless possible universes, making it hard to test. Yet the payoff could rewrite physics. If quantum gravity explains acceleration, we might not need dark energy at all, just as Einstein's relativity made Newton's action at a distance gravity obsolete. The universe's expansion could be a side effect of spacetime's true quantum nature, hidden in plain sight until we learn to see the threads. The deepest clue might lie in black holes. Both theories predict these cosmic pits distort spacetime's quantum fabric in extreme ways. Future gravitational wave detectors could spot anomalies when black holes merge, tiny deviations from Einstein's predictions that reveal whether strings or loops are steering cosmic growth. Until then, the expansion puzzle remains a battleground for ideas, where the tiniest specks of quantum reality might hold the key to the universe's largest scales. And somewhere in that quantum haze, dark energy's days as a placeholder may be numbered. What if our universe's expansion rate isn't just a cosmic accident, but the winning ticket in a multiverse lottery? Imagine a vast sea of universes, each with its own laws of physics, where some expand too fast for galaxies to form, others collapse instantly, and a vanishingly rare few hit the Goldilocks zone where life becomes possible. This is the multiverse hypothesis, and it offers a startling explanation for why our universe's expansion rate seems so finely tuned. If dark energy were even slightly stronger, galaxies would have been ripped apart before stars could ignite. Slightly weaker, and gravity would have crushed everything back into a singularity. Yet here we are, in a universe where the numbers align just right, not because of design, but because we couldn't exist in any other kind. The anthropic principle cuts through the fine-tuning puzzle like Occam's razor. Instead of asking why our constants are so precise, it flips the question. We can only observe a universe capable of producing observers. Picture a room filled with clocks, all broken and stuck at random times. If you check the time, you'll only ever glance at the one clock that happens to be working, not because it's special, but because it's the only one you can read. Similarly, in a multiverse where expansion rates vary wildly, only the universes with conditions permitting life will ever have astronomers to measure them. String theory's landscape fuels this idea with mathematical heft. The theory allows for 10 to the power of 500 possible vacuum states, each representing a distinct universe with different constants. In this cosmic buffet, our universe's expansion rate might simply be one dish among countless others, most of them inhospitable. Eternal inflation takes it further, suggesting new universes bubble up endlessly, each with random properties. Some might have dark energy so weak they collapse in seconds, others so strong atoms never bond. We don't see those failed experiments because they're sterile, leaving only the successful ones to tell the tale. But the multiverse isn't just a philosophical escape hatch, it makes testable predictions. If our universe is one of many, collisions with neighboring bubbles could leave scars in the cosmic microwave background, like bruises from a cosmic bumper car ride. Some researchers claim to spot these anomalies in the CMB's cold spots and asymmetries, though the evidence remains controversial. Others hunt for indirect signs, like unexpected patterns in gravitational waves that might betray higher dimensional leakage from adjacent universes. The real mind bender: if the multiverse exists, there could be universes where dark energy's strength changes over time, or where expansion reverses mid-game. Some might even harbor life adapted to wildly different physics, beings swimming in plasma clouds or surfing the shockwaves of eternal inflation. We'll never visit these alternate realities, but their hypothetical existence reshapes how we view our own place in the cosmos. Not as the center of everything, but as a single page in an infinite library, where the book we're reading just happens to have a story we can understand. Critics argue this is little more than sophisticated guesswork, that invoking a multiverse explains nothing if it can't be falsified. Yet as puzzles like the Hubble tension and dark energies bizarrely small but non-zero value deepen, the multiverse remains the most expansive canvas we have to explore them. It doesn't solve the mystery so much as reframe it, turning fine-tuning from a miracle into a selection effect. After all, in a cosmos where anything can happen, we were bound to find ourselves in the one where everything worked out. The question isn't why our universe expands the way it does, but how many others out there never got the chance to ask. So there you have it, 30 mind-bending facts about the universe's expansion, each one a jagged piece of a puzzle we're still assembling. From Hubble's groundbreaking discovery to the whispers of quantum foam, from the ghostly pull of dark energy to the cosmic echoes frozen in the CMB, we've traced the contours of a mystery that defies simple answers. Yet for every fact we've uncovered, a dozen questions remain. Is dark energy truly constant, or does it pulse and fade like the tides? Are we floating in a cosmic void, skewing our measurements? Could the Hubble tension be a crack in Einstein's unshakable relativity, or just a glitch in our telescopes? The beauty of cosmology is how much space it leaves for wonder. Those distant galaxies racing away faster than light, the quantum ripples that seeded all structure, the eerie fine-tuning of the universe's expansion rate, they're not just dry data points. They're invitations to explore, to question, to imagine. Maybe you think dark energy is the heartbeat of a higher dimensional universe, or perhaps you suspect it's the shadow of some undiscovered particle. Whatever your theory, the cosmos isn't done surprising us. New telescopes from JWST to the upcoming Vera Rubin Observatory are peeling back layers of this mystery even now, and who knows what they'll reveal next. So here's where you come in. What's your take on the universe's runaway expansion? Do you buy the multiverse explanation, or is there a simpler solution hiding in plain sight? Drop your wildest ideas in the comments. We're all detectives in this cosmic whodunit. And if you're hungry for more space mysteries, hit that subscribe button. The universe isn't just expanding, it's unfolding, and we're just getting started.